Good morning, everyone. So, we looked into, we are continuing with the membrane based separation processes, and we have looked into several aspects of membrane based processes, various definitions, and basic modeling, one dimensional modeling, so on and so forth. Now, in this class we will look into some more definitions and various transport phenomena, those will be involved in the membrane based processes. So, the first aspect that we will be looking into in today's class, fluxes and driving forces involved in membrane based processes. Now, we already looked into the definition that separation of species occurs because of difference in transport rate. Rate of chemical species through the membrane. This depends on two factors. One is the mobility of the species, another is the concentration. Now, mobility will depend on the solute size and structure of membrane, and concentration, of course, it will depend on the chemical compatibility and interfacial properties. So, let us elaborate on this. Now, mobility of the species will depend on the solute size and structure of the membrane. If the solute size is small compared to the membrane size, for example, we were talking about let us say a salt solution, salt species in microfiltration membrane. In microfiltration membrane, the pore size is extremely large. On the other hand, the salt size is pretty small. So, there will be almost convection of the salt through the membrane pores. On the other hand, if the species size is compared to the size of the membrane pores, then there will be hindered diffusion. So, there may be hindered diffusion, there may be free diffusion, that means it is a free convection case in case of solute. Depending on the solute size and the size of the ratio of the solute size to the pore size, the mobility of the species becomes very important. And concentration of the species through the membrane phase will entirely depend on the chemical compatibility and interfacial properties. For example, if we have a solid which is hydrophilic in nature, and if you have the material of the polymer which is hydrophilic, okay, so that will be more amenable to move through the membrane phase. If the solute is hydrophobic, then it will not be liking the hydrophilic environment of the polymer. And similarly other things. So, chemical compatibility and interfacial properties, hydrophilicity, hydrophobicity will become very important as far as the specific transport rate of the species are concerned through the membrane phase. Okay. Now, let us look into the basic forces of the transport. That means there is a flux, means there is a driving force. Okay. Unless and until there is a driving force, you could not have flux of any material. Flux means volumetric flow rate per unit cross sectional area normal to it. So, let us look into the various basic forces of transport through the membrane phase. Now, what is the driving force? I think we have discussed it earlier. Driving force will be nothing but the gradient of chemical potential. Now, this gradient of chemical potential will be having there three components. One is the pressure difference, pressure gradient, concentration gradient, and temperature gradient. You can have an electrochemical electric potential gradient as well. Now, typically chemical potential will be having three components: pressure, concentration and temperature for a neutral solute. But if you have a charged species, for example, if you are talking about the transport of a salt which is a charged species, that means electrolyte, through a nanofiltration membrane, then electric potential gradients becomes very important for transport of electrolytes through nanofiltration membranes. Then electric potential gradient becomes important. Otherwise, there will be three components: pressure, concentration and temperature. All these three will constitute the chemical potential gradient. Now, among these three, for a neutral solute, now among these three there may be one driving force may be present, that means pressure gradient may be present, there may be concentration gradient may be present, there may be temperature gradient present individually, or maybe two of them or three of them all together. Okay. Now, the various transport laws through the membranes are classified into several categories. The first one is passive transport. In passive transport, the solute will be transported through the membrane phase by electrochemical by gradient of chemical potential, and mu a prime is chemical potential in feed stream, and mu a double prime is chemical potential in permeate site or in the downstream. If mu a prime is greater than mu a double prime, then we call it a passive transport. This is a normal case. The driving force is more in the upstream compared to the downstream. So, there will be transport of species from the upstream to the downstream. So, that is called the passive transport, and it is a normal circumstances. Now, second one is facilitated transport. In this case also, the transport is from higher chemical potential to lower potential chemical potential, but the transport is facilitated by an external agent or a third agent present in the membrane phase. For example, the species A has to be transported from the feed site to the permeate site. The chemical potential in the feed site is mu a prime, and that is permeate site is mu a double prime, and of course, mu a prime is greater than mu a double prime. Okay. But the point is, there is an agent present, agent B is present in the membrane phase, which forms a complex A plus B with the permeating species A in the form of a complex AB, and that will be transported. So, here the transport rate will be more. Why? Because when A is coming into the membrane phase, it forms a complex AB. Therefore, the concentration of the species A in the membrane phase will be immediately 0. So, it maintains a maximum concentration difference between the membrane phase and the feed phase. So, therefore, more A will be coming into the membrane phase and the transport rate will be enhanced. Now, in the downstream, there is no A present at all in the membrane phase. So, there exists a stiff concentration gradient of species A from the in the membrane phase, in the polymer phase, from the feed site to the permeate site. Because of this gradient, this concentration driving force, the species will be transported towards the permeate side, and in the permeate side there is no A present. So, again it will be dissolved. So, basically AB, the complex AB again breaks down. This is a reversible one. The complex AB breaks down and the species A gets transported on the permeate side. Because of the presence of this external agent B in the membrane phase, the transport rate of A is facilitated. The selection of the species B is such that it has a higher it cannot go into the feed stream or it cannot go into the permeate stream. It will be within the polymer phase. So, this is known as the facilitated transport, and so it is a special form of passive transport. Okay. The third transport mechanism is known as the active transport mechanism. In this case, the species is getting transported against its driving force. So, that means in the feed side the chemical potential will be lower compared to the chemical potential in the permeate side. So, mu A prime is much less compared to the mu A double prime. How it can happen? The species A gets transported from the feed to the permeate side. Here also there is an agent present within the membrane phase and there is a reaction going on, A plus B going to AB. Okay. Now, activation energy of the chemical reaction provides the it provides the driving force to transfer activation energy of reaction in membrane phase provides energy to transport of A to the permeate site. This occurs in most of the living cells. So, once we identify so these are the various transport laws which will be mechanisms which will be encountering in membrane based processes, and in our course we will be basically looking into the first two transport laws. One is the facilitated transport, another is the passive transport. Now, we can now describe the transport process by phenomenological equation. Now, phenomenological equation is very important. This equation gives a relation between the flux and driving force. This is also known as cause-effect relationship. This cause-effect relationship only says that there is a flux of a species if there is a driving force present in the system. See, it is basically the natural phenomena. That is why these equations are called phenomenological equations, and they are basically proportional. Flux is proportional to the driving force. Now, the proportionality constant becomes very important, and it is a property, it is a specific property to the system that we are studying. Now, you have already studied various phenomenological equations. I will just give some examples and try to summarize this. Phenomenon involved flux, driving force, constant or proportionality, that becomes a property of the system. The first phenomena you know is a Fick's law. The flux is mass flux, and what is the driving force? Concentration difference, concentration gradient. And what is the constant of proportionality? That is diffusivity. Second one is Ohm's law. The flux is basically electricity, charge per unit time. So, it is basically current, and driving force is basically electric potential difference gradient. And what is the constant of proportionality? It is the resistance, right. Third one is Fourier's law. The flux is heat flux, driving force is temperature gradient, and constant of property is thermal conductivity. Now, these properties of the proportionality constant becomes the property of the particular system. It becomes a constant property of a particular system: diffusivity, resistivity, and thermal conductivity. In membrane based separation processes, we have several driving forces. For example, main driving force is chemical potential, but chemical potential is an abstract thing. It has generally three components for a neutral solute, as we have discussed earlier: concentration, pressure, and temperature. Now, one of these two, the driving forces may be interdependent or they may be absolutely independent. Okay. Now, let us look into the cause effect relationship in membrane based processes. Concentration gradient across membrane leads to flow of matter. That is obvious, right? You will be getting a mass flux if there is a concentration gradient, but at the same time it gives it results into a build up of pressure. It results a build up of pressure, or there is a difference in pressure, or pressure gradient will exist. Okay? Because why the pressure gradient will exist? Because of the concentration gradient, more matter, more species will be transported towards the membrane, leading to a high concentration of the solutes on the membrane surface compared to the bulk. Okay? Now, high concentration of the solute at the membrane surface means its osmotic pressure will be more, because being a colligative property. So, there will be a difference in pressure between the bulk and the membrane surface. So, this phenomena is known as, and that pressure is known as the osmotic pressure, and this phenomena is known as osmosis. A pressure difference leads to volumetric flow plus concentration difference. This is a case of reverse osmosis that we have already discussed. Okay. Temperature difference across the membrane obviously temperature difference will give you a heat flux plus as well as flow of matter. That simply means if you do not do anything, if you just maintain two different temperatures in the feed side as well as in the permeate side, there will be a flow of matter. the solvent will be moving from the feed side to the permeate side, along with the heat flux. Since there is a temperature difference, there will be a heat flux because by the Fourier's law. This combined effect is known as the thermodiffusion or Sorey effect. Similarly, concentration difference across the membrane will give rise a mass flux plus a temperature difference. Okay. This is just opposite to the Sorey effect and it is known as Dufour effect. Okay. So, in membrane based processes there may be several driving forces present and they will lead to several phenomena which may be interdependent or dependent. Okay. So, let us look into the osmotic pressure, the thermodynamic from the thermodynamic angle, the definition of osmotic pressure. Okay. We will do the same we will take the same example that we have taken in the last few classes, that we will be having two chambers separated by a semi permeable barrier or a semi permeable membrane. The side A is pure solvent and chamber B will be having a solution. Okay. So, let us use this notation 2 for solvent and 1 for solute. Okay. P1 is pressure in chamber A and P2 is pressure in chamber B. Now, at osmotic equilibrium, the chemical potential of the solvent is equal on both the chambers. Okay. Now, this equation can be written as mu 2 is equal to mu 2 naught plus RT ln A2, where mu 2 naught is for pure solvent, chemical potential for pure solvent, and A2 is solvent activity. Now, we do a hypothetical experiment. What do we do? In one of the cells we put some sodium chloride, okay, and see what happens. So, initially both the chambers, both at pressure P1, right, and mu 2 is same in both the chambers because they are both pure solvent, okay, pure water. Mu 2 is same in both. That means initially we had pure solvent on both the chambers. Now, we add a small amount of solute in chamber B. So, B becomes a solution. Now, it remains no longer a solvent, it becomes a solution, and mu 2 0 P1, because it was pure solvent. So, it is mu 2 0 P1 becomes mu 2 at P1 in chamber B. We still keep the pressure P1 in chamber B. Now, mu 2 at P1 becomes mu 2 0 P1 plus RT ln A2. Okay. Now in B we apply pressure so that P1 becomes P2 and osmotic equilibrium is restored. Why you are applying pressure? Because when you are adding a salt in chamber B, more solvent will be coming from because solvent concentration is less there. So, more solvent will be coming from the solvent side to the solution chamber from A to B. Now, you are applying pressure in chamber B and raise it pressure, so that the solvent flux will be arrested and an equilibrium of the equilibrium will be restored, that is known as the osmotic equilibrium. Okay. So, therefore, at osmotic equilibrium you can write mu2 at P1 in B is equal to mu2 at P2 in A. Okay. So, this becomes mu2 naught plus RT ln A2, mu2 naught at P2 plus RT ln A2 is equal to mu2 naught at P1, because in chamber P1 we had the pure solvent. Now, we rearrange this equation, and rearrangement results mu2 0 at P2 minus mu2 0 at P1 will be equal to minus RT ln A2. Okay. Now, we invoke the definition of partial molar volume. What is the definition? Vi bar is basically partial molar volume of ith species. This is nothing but del mu I naught del P at constant temperature and concentration. So, this equation can be written as mu 2 naught P2 minus mu 2 naught P1 is equal to P1 integration from P1 to P2 V2 bar dP. Now, we assume that the molar volume does not change over the range of pressure P1 to P2. That means, V2 bar can be treated as constant. So, it will be nothing but V2 bar times P2 minus P1 if it is treated as constant within the small region. Okay. So, therefore, now we can combine this equation, and what is P2 minus P1? This is nothing but the osmotic pressure, because you are restoring the osmotic equilibrium. So, now combine this equation and this equation, you will be getting V2 bar times pi is equal to minus RT ln A2. So, this will give a direct relationship of osmotic pressure with the activity of the solvent and temperature, and of course, the molar volume of the solvent, and pi becomes minus RT by V2 bar ln A2. Okay. So, what is A2? A2 is basically solvent activity. This is nothing but solvent vapor pressure in presence of salt and this is pure solvent vapor pressure. So, you will be having Ps divided by Ps star, and pi becomes RT by V2 bar ln Ps star by Ps. Now, it is not always desirable, or you will be getting the data of solvent vapor pressure in presence of salt and pure solvent vapor pressure different temperatures, and it will entirely depending on the salt concentration, so on and so forth. So, therefore, more amenable form of osmotic pressure with concentration, because solvent vapor pressure in presence of salt is entirely a function of the salt concentration. Okay. So, it becomes very difficult. So, directly there are some amenable form of osmotic pressure with concentration are given, pi is equal to RTC for this here C is the concentration is the in molar unit, molar concentration. This for the dilute solution or for the salts, and pi becomes B1C plus B2C square plus B3C cube for concentrated solution of proteins, so on and so forth. And this corroborates the fact that osmotic pressure is a colligative property and it is a function of concentration, and we have discussed in detail how what are the range of applicability of linear relationship of pi versus C like RTC, and a nonlinear relationship as a function of polynomial with concentration probably in the last class. Now, once we identified that osmotic pressure becomes a vital factor or parameter in case of reverse osmosis, where the pore size is extremely small, the smallest possible pore size we can talk about in membrane based separation processes. For example, sometimes the pore sizes are so small, it is 2 to 10 angstrom. Okay, the pore size is so small, sometimes the reverse osmosis membranes are called impervious membranes, non-porous membranes. Sometimes you can come across in literature non-porous membrane. Non-porous membrane means it is basically if they are talking about reverse osmosis membrane or gas permeation membranes. Okay. Now, we will look into, so osmotic pressure becomes very important as far as the transport of reverse osmosis is concerned. Now, we will look into the transport rates or transport laws through a reverse osmosis membrane. First, we talk about the transport of solvent and solute both. Okay. Now, there are certain assumptions before we start looking into the theory. What are the assumptions? Flux of ith species. What are the ith species? Different species, one is the solvent and there is the solute. Okay. Ith species may be a function of various forces present in the system, number 1. Number 2, under condition not far from equilibrium, flux force relationship is linear. So, therefore, we can write Ni is the flux of molar flux of any species will be a summation of Lij times Fj. Okay. Ni is flux, molar flux of ith species Fj will be the jth driving force, and this summation is over j 1 to n. Let us say n number of driving forces are present, maybe concentration difference, maybe pressure difference, so on and so forth. And Lij are basically the proportionality constants, and more often they are known as phenomenological constant. Because this relationship is derived from the phenomenological equation that I have discussed in the start of the class. And another assumption is that we assume no other external force present in the system. To influence the transport of the species. Okay. Now, let us write 1 for the solute and 2 for the solvent. So, therefore, the solvent flux can be written as minus L21 gradient of mu 1, that is the potential gradient, minus L22 gradient of mu 2. The force is nothing but minus of gradient, right. So, therefore, N1 can be written as minus L11 gradient of mu 1 minus L12 gradient of mu 2. Okay. Now, there is something called Onsager's reciprocal principle, reciprocating relationship. This says that if fluxes and forces are appropriately selected, if fluxes and forces are appropriately selected, that means for proper selection of the flux and force, Lij is equal to Lji, that means cross coefficients are equal, and we assume that and there is another definition is for coupling. Coupling says, coupling is basically the influence of a driving force on the species of the other. That means the influence of a driving force that is acting on species 2 that may influence the transport of species 1, that is called the coupling or relationship between the two. And we assume that in case of reverse osmosis there is no coupling. Okay. That means L12 and L21 will be equal to 0 in this case. For if we assume there is no coupling or coupling will be extremely small. In that case, the solvent and solute fluxes becomes N2 is nothing but minus L22 gradient of mu 2 and N1 becomes minus L11 gradient of mu 1. And if you look into the definition of chemical potential, gradient of mu 1 is nothing but del mu I del P, constant temperature and species concentration, gradient of P plus del mu I del C I P and T, gradient of C I. Now, there should be one more term, that is the gradient of temperature, but most of the reverse osmosis and membrane based processes they occur under isothermal conditions. So, temperature gradient will be negligibly small and they will not be present at all. There may be another term, that is for the electrochemical potential gradient if we talk about motion or the transport of a charged solute in a charged environment. For example, motion of the transport of electrolyte in case of charged nanofiltration membrane. Okay. Otherwise, there are two main driving forces are present, is delta P and delta gradient of pressure and gradient of concentration. Now, in terms of this, the solvent gradient can be written as minus L22 del mu 2 del P gradient of P plus del mu 2 del C2m gradient of C2m. Now, what is C2m? C2m is basically the molar concentration of solute in barrier, that means in membrane phase. If you remember, we are writing the transport law of the solute and solvent within the membrane phase. Okay. In our system, we will be having this is the membrane phase, this is the feed side, this is the permeate side. Okay. So, this is x is equal to L, x is equal to 0 and this is x equal to L. What is L? L is the thickness of the membrane or the barrier, and C2m is the concentration over here in the membrane phase. That means concentration of the solvent in the membrane phase, and you will be having a concentration in the upstream C2m prime and a concentration of solvent in the downstream C2m double prime. Okay. That is at the interface of the bulk and the membrane. Okay. So, this is basically steady state case. The equation can be integrated across the integrate the earlier equation across membrane thickness. What you will get? N2 dx is equal to minus L22 gradient of mu2 del C2m d C2m from C2m prime to C2m double prime from the feed to the permeate side, that means from x is equal to 0 to x is equal to L, plus this should be bracket here, plus del mu2 del p dp p2 to p1. P2 is the feed side, at higher pressure because it is reverse osmosis membrane, and P1 is pressure in the permeate side or permeate side pressure, and P2 is greater than P1. Okay. Now, we invoke, and at the steady state N2 will be equal to N2 is constant. Okay. And now, we invoke the definition of partial molar volume. V I bar is equal to del mu I del P for a constant temperature and species concentration. So, what we will be doing will be let us integrate it out and see the result what we get. We get after integration N2L minus L22 integration C2m prime to C2m double prime del mu2 del C2m dC2m plus del mu2 del P dP from P2 to P1 bracket end. Now let us look into the some of the relationship. At osmotic equilibrium, what happens? At osmotic equilibrium, we have found out that the solvent will not be passing through permeating from the feed side to the solution side. That means, the solvent flux will be equal to 0 because it is at equilibrium. The solute is not allowed to pass at all. The solvent flux will be equal to 0. So, what does that give? That will give us, if you put the value of del mu to del P as V2 bar, the molar volume, and we are assuming that over the pressure difference P1 and P2 molar volume does not change. From this above equation, what you will be getting is that V2 bar P2 minus P1 will be nothing but integral C2m prime to C2m double prime del mu 2 del C2m d C2m. So, and what is this P2 minus P1? This is nothing but the osmotic pressure difference. So, this is basically the osmotic pressure difference between the permeate and the feed C2m prime to C2m double prime del mu 2 del C2m d C2m. So, this equation gives a closure to the above to the integration. Now, you can substitute the value of this quantity in the governing equation and see what you get. Now, if you do that, that means I am going to substitute this the whole term, this equation, by V 2 bar times delta pi, that gives a closure. So, N 2 L will be nothing but minus L 2 to V 2 bar times delta pi minus integration P 1 to P 2 V 2 bar dp. Okay. Now, we assume that V 2 bar is constant over the pressure range P 1 to P 2. So, it is becomes L 2 to V 2 bar divided by L, N 2 becomes, this is nothing but delta P minus delta pi. Here we have just inserted, so it gives a, with an algebraic manipulation you will be getting this expression. So, what this expression represents, this expression gives a relationship of the solvent flux through the membrane, okay, and it is proportional to delta P to minus delta pi. What is this delta pi? Delta pi is basically the osmotic pressure buildup that has to overcome by using your operating pressure, okay, and whole these constants, this whole thing, this becomes a constant for a particular membrane. For a particular membrane, the thickness is constant, L22 is the phenomenological constant, V2 bar is the molar volume of the solvent. And if you so what is the unit of N2? The unit of N2 will be mole per meter square per unit time. It is the molar flux. You can convert it into the volumetric flux by multiplying with the density and the molecular weight. So, this becomes N2 becomes let us say J is nothing but volumetric flux and a group of constants. So, it will be another constant times delta P minus delta pi. This constant is known as the permeability if J is expressed as a volumetric flux. That means meter cube per meter square per unit time. You can easily convert mole per meter square second into meter cube per meter square second by invoking the factors of density, molecular weight, so on and so forth. Okay. So, J becomes LP times delta P minus delta pi. Okay. This LP is known as the membrane permeability. So, this relation gives the solvent flux in case of reverse osmosis through the membrane, and this is known as osmotic pressure relationship. Or phenomenological equation, logical equation for porous membranes. It has another name, Darcy's law. Okay. So, volumetric flux of the solvent is proportional to a driving force. The proportionality constant is the membrane permeability. So, we had the proportionality constant as diffusivity in case of Fick's law. We had the proportionality constant as thermal conductivity in case of Fourier's law. We had the proportionality constant as resistance in case of the Ohm's law. We had the proportionality constant as membrane permeability in case of Darcy's law. Okay. Fine. Next, we look into the solute flux. Through the membrane. The assumptions involved are same: steady state, one dimensional flow, one dimensional transport, and there is no coupling. Okay. So, we go back to the equation of the solute flux and integrate it. The solute flux expression over membrane thickness. If you do that, what you will be getting is N1 dx 0 to L is minus L11 C1m prime to C1m double prime del mu 1 del C1m, okay, dC1m plus del mu 1 del P dP from P2 to P1. Okay. So, you will be getting as L11 C1m prime to C1m double prime with a minus sign here, del mu 1 del C1m dC1m plus V1 bar L11 delta P. Okay. So, we assume we invoke the definition of the molar volume of the solute and include the and replace del mu 1 del P in terms of the molar volume. Okay. So, I think we require some more time to discuss this issue and get along the derivations. We will discuss in the next class, and we will arrive at an expression of solute flux through the reverse osmosis membrane. So, we got the expression of the solvent flux through the reverse osmosis membrane. We will be getting the expression of solute flux to the reverse osmosis membrane. For the first case, the solvent flux, you will get an idea what will be the productivity of the system, how much meter cube liter per hour you can process. Okay. In the second case, when you will be getting the solute flux to the membrane, you will be getting an idea what will be the quality of the permeate. First one I talked about the productivity, it is the quality, it is the quantity, and the next one it will be the quality. What will be the rejection, what is the quality, what is the amount of permeate concentration of the solute present in the permeate stream, whether that is admissible or not, those decisions one can make. Okay. Thank you.